Sorry, you're all walking out of class, I'm sure. Walking is part of the formal tradition of going to college and all that stuff. Nobody yet? Okay, we'll get you next time. I'll have you next year. So, thank you for these. How are the quizzes, okay?
They were good.
Just a pair, right? Just a pair of them?
Yeah, they're just two.
Just two of them. One's the Ben Snowfall I had to go with. I had to play with that just because of that one freakish day we had
I looked at it.
in February. You remember that day?
Oh, yeah.
2.5 feet of snow, whatever it was, depending on where you were, I guess. It could have been more or less. But it was interesting because that day I was out there shoveling and I just injured my shoulder. So I was thinking about, I don't know, trying to think about something else besides how much my shoulder hurts. And I was like, let's make a great quiz because I have all this old snowfall data and I've got averages from all these years. And I went back inside to send myself an email to remind myself to do that, and I had an email or two, I forget, from students in 243 last term going, I wonder what the average snowfall is now with this, and I'm like, I love it. I'm infecting you guys and making you think about this all the time, even when you have a snow day on Saturday. So, it was fun. It's fun. It shows you the effect that one large data point can have on a data set. And large is a relative term. I mean, we're going to see something right here momentarily, but, and then the other quiz was just too much fun not to, especially when I was talking about fishing. It's 2 feet on average. It's tricky. That's tricky. You still drown in 2 feet of water, and you can definitely drown in an average of 2 feet of water. Yes. I mean, we've heard it many times. You can drown in 2 feet of water. But you can drown in an inch of water. Then you fall, right? Knock yourself out. Exactly. But you can definitely drown in an average of 2 feet of water. And looking at the pictures you guys drew, some of you drew pictures. I can totally tell you got the point. You totally got the point about an average and how it's different than a data point. Nice. Very nice. Very nice. Speaking of averages, I wanted to come back to this. I promised you guys I would look at... How's this working? That's a little better. I reworked the data on this graph a smidge, just a smidge. I want to let it go after that because I liked it because our data is starting to look bell-shaped. We look like we're almost bell-shaped height-wise. And I remember we approximated our averages. I had you guys kind of ballpark where you thought the averages were last class. And you guys guesstimated about a 5'4" or 5'3" average for the girls. And you guesstimated about a 6 foot tall average for the guys. I went ahead and calculated the average using the weighted mean idea in Excel. Girls 64.18 using the exact precision that I'm not allowed to. 64 inches, that's 5'4". Nice work. You guys nailed it within 1/10 of an inch according to Excel. And the guys, we said it was 6 feet. Yes, we said it was 6 feet. Excel says 71, which is just a smidge below 6 feet. Yes, 6 feet would be 72. So again, I mean, it's not much below, so again, nice. This is when you can get close and not have to worry about exactness. If you need precision, you have a tool to use it, whether it's your TI, whether it's Excel, whether it's other kind of computing. But you can also get those measures from the graph itself without even using the data, which is kind of slick. The thing that I was really impressed with you guys, though, I'm going to brag about you a little bit, YouTube world, was you approximated the standard deviation of both of these graphs. Do you remember doing that? This took a little bit more. We just learned about standard deviation, and it was still kind of like fresh in our minds, not to mention the fact that it's a little bit, it's because averaging has been done in your lives for so long, standard deviation has to become comfortable. It has to become part of our conversation. So what was that wonderful guideline we learned last time about bell-shaped data? Do you remember? If, big if you have bell-shaped data, Zach.
Go out to the ends.
And the ends would be what-ish?
Whatever the maximum.
And what would that be if you go out to the, here's what Zach is saying. He's saying, here's your data, go out to the ends. This works great on small data sets. What would that represent then, Zach?
The range.
What range? I love what you're saying.
Height.
Good. So quantify it using standard deviations for me. We were using a ballpark of 2 standard deviations for that. Now, as the data sets get larger, it gets harder and harder to find the ends. Generally, as the data sets head off towards infinity, these bell curves begin to tail off. Okay, you eventually get people that are 7 feet tall and people that are 4'6", and they begin to tail off. So you might not want to go out to the ends every time, but 2 standard deviations. Who said this? Somebody said it very, very well last time. 2 standard deviations separates the what from the what. I want to start using this word before we'll formally define it in about a week, but what does 2 standard deviations in a bell curve do? It separates the ba from the ba. Do you remember the word we used?
Middle average.
Good. Outliers. It separates the outliers from the averages. So when we say average, there is one average of the data set. So for girls, it's 64 inches, 5'4". Would you call a 5'3" girl significantly smaller than a 5'4" girl? I wouldn't. It's close. She's close. She's an inch different. How about 5'2"? How about 4'8"? Well, see, now you're getting into like, okay, gut feeling is saying that's probably smaller than average. Maybe there's something genetic, maybe she hasn't fully grown yet, whatever. Guys, okay, guys, we're average is 6 feet, we said, right? About 6 feet, 5'11", 6 feet, somewhere in there. Would a dude that's 6 foot tall exactly be unusual? No, how about 6'1"? How about 6'2"? How about 6'8"? Yeah. Then you're like, okay, why is he so tall, right? Why is he so tall? Then you start asking questions. That's what statistics is great at, you know?
Oh, yeah, I was at thrift fair the other day, and I think the guy was 6'6".
Yes!
So I didn't even reach his shoulders. Like,
when I play with Necktie Killer, I feel short. I'm 5'11" and a half. The average height of that band is 6'3". I've calculated. They're huge dudes. Steve Miller, he's this wide dude. I mean, they're huge, and I have to wonder, why the hell? I have no explanation other than Redmond High School. That's just the only thing different between me and them is Redmond High School. But they're this huge, tall band. But what's interesting is, when I first started playing with them years ago, they were all that tall. Little by little, people have flushed out of the band and flushed back into the band, and now more normal-sized guys are flushing into the band, and the average height is falling. It's still 6'3", whatever I just said it was. But it was much higher than that before. So I do think it was fluky that there were so many tall people in that band originally. I just happened to walk into it. But again, there is a gut feeling you have once you get past that 2 standard deviations. So what Zach said, I love, go out to the ends, call that 2 standard deviations. And then we did that quick calculation, right? Quick calculation. 5'0" to 5'9", that's 9 inches, correct? Now if that's 2 standard deviations, I want to do a quick calculation on the board. Not much of a calculation, we did it last time. 2 standard deviations. This is an important one to keep in our mind. Of all those standard deviation rules we filled that board with, this is probably the most important one. That's x bar plus or minus 2 s's, yes? So what that does is it slaps x bar in the middle, and then it goes out 1 standard deviation and then a second, and it goes down 1 standard deviation, whoops, and then a second. So in other words, when you've done that with your hands, the 2 standard deviations, this 9 inches, this is 9 inches according to our graph right there, yes? How many S's have you gone? You've gone 4, haven't you? X bar, up 1 S, this is an S right here. That's an S. You've gone an S more here, so 2 S's that way. And you've also gone an S this way and then an S this way. There's 4 S's altogether. So if you've gone 9 total, divided up into 4 pieces, how big is each S value? 2.25, remember? That's what we ballparked in class. I went back to Excel, had it calculated. Check you guys out. Look, yeah, oh wow, indeed. I almost peed myself when I hit enter. I almost peed myself when I hit enter. Freaking awesome. Now, we said the same thing for the guys, didn't we? Didn't we say the same thing for the guys? We did the exact same thing. Now notice the guys is 3.12. We were off a little more on that one. Can you see why? We were off on the guys versus the girls. There's a data point we didn't include in our calculation that the formal standard deviation calculation will. We did the exact same range. We said here to here is normal, which I believe was, what is that, 5'8" to 6'5", or 5'7" to 6'5", which I think is 9 inches again. But we ignored this 5'4" down here. If you include that in the formal calculation, it means they're a little bit more spread out than we took account for. Yes? So by ignoring that, we termed it an outlier. By ignoring that, we also shorted the standard deviation a little bit. But we still got damn close. It's not like we said 2.25 and it was actually 6.8 or something like that. If you trim off the outliers, generally there aren't going to be that many of them, so you can trim them off safely. So I was wicked impressed with how you guys came up with that. Cool. Now, I also grayed out some stuff. This was a perfect place to stop last time. See all this stuff that's grayed out back here? You can't right now because I grayed it out. There's some really funky calculations in there I want to come back to. Because getting standard deviations from raw data, we already know how to do that with Bert and Ernie. We already did it, right? Bert and Ernie. Put the data in, subtract the average, square, divide, square root, done. I say that now. We did it about a week ago. You suffered through it once, you'll never suffer through it again. Because now, you go to one of our stats and we're done. Yes, done. How do you do standard deviations when you're given something like this? Like if you actually need precision, like if you can't just go, 9, if you actually need like a precise standard deviation measure. How do you do it? So we're not going to use this. This is too messy. There's too much data here. I've got a smaller data set I want to play with you guys. So let's mute this for now. Do you guys have the data sheet with you? If you didn't get it last time, I'm sure I brought extras. Let me just find it. Put this one here. Anybody need these from last? Okay, so here, grab. They printed poorly. I apologize. Grab. Yeah. Top and then the next page down here. Nope.
Thank you.
Yeah, and just send them that way. If anybody else needs them over there. And then I got a stapler here somewhere. Here we go. Staple them together. There we go. So what I've got on that data sheet